Now we are going to use Gauss's law to calculate electric field due to a symmetrically charged distribution. And in this case we are taking an insulating solid sphere, and it has a charge distributed over it which is uniformly distributed over the surface. So in the first case, now suppose that you have a sphere and positive charge is uniformly distributed over this sphere. And now suppose that at this point we need to find out what is the electric field. And the total charge on this sphere is plus Q. And it is distributed all over the sphere very uniformly. Now you know that whenever we have a uniform charge distribution, we can use Gauss's law for it. And the first step in Gauss's law is to draw a suitable Gaussian surface over it, imaginary surface, which is also called Gaussian surface. So we'll draw a surface over it. But before drawing a surface, I would like to explain you how the electric field will be, because you see it's a positive charge, so electric field will be radially away from it. So from every point, electric field will be away from this sphere. Okay, so this will be the electric field due to this positive charge distribution. Now at this point we are going to draw a Gaussian surface. So on this Gaussian surface, now at this point we know that the electric field is radially outwards from the surface, and because it is a sphere, so the area vector will also be along the radius of the sphere. So if this is the radius, area vector will also be in the same direction. Okay, or we can say the dA vector, if we are talking about a small area on the surface, will also be in the same direction. So we now know that electric field and area vector, they are parallel to each other. Okay, and we have drawn a Gaussian surface. So if they are parallel, it means that theta is 0, and integral of E vector dot dA vector will be, now because we are talking about a surface which is closed, so we say it is EdA. Another point to understand here is that if this distance is r from here to the center of the sphere, okay, if this distance is r, even this will be r. Okay, so the electric field on the surface will be constant because it depends only on r, and the charge is constant, r is constant. So we can take electric field to be outside, and it will be integral of dA. Now because it is a sphere, so you know the surface area of a sphere is E into 4 pi r square. Now this is the left hand side of the equation. Now what is the total charge enclosed by the surface? So this is our Gaussian surface, and inside this surface you have this total charge. Okay, so the total charge will be plus Q. So then now we'll be putting these values in the Gauss's law equation. So it will be charge enclosed by epsilon naught, and so it will be E into 4 pi r square upon Q upon epsilon naught, or E is equal to Q upon 4 pi epsilon naught r square. So this will be the electric field due to this charge distribution on outside the sphere. So this is valid, this equation is valid Now the radius of the charge distribution is A. Okay, and so this equation is valid for R greater than A. Okay. Now in the similar manner, let us also solve it for a point which is inside this sphere. Now let's say we have the same sphere and it has the same parameters. The radius is A, and now we have to find out what is the electric field at this point inside this sphere. Okay, so for the first case, R is less than A. Okay, for this case, for the first one R was greater than A, and this for the second case R is less than A. Okay, so now if we have to find out what is the electric field at this point, first thing we do is we just make a imaginary surface. We just draw imaginary surface over it. Now we already know that it is positively charged, so the charge will stay the same everywhere. It is the same, but the only difference being that the total charge on this sphere is capital Q. We already know it, which is same, and it has a volume of V. Now you know that the volume of this sphere will be 4 upon 3 pi A cube, because it has a radius of A. But now we are talking about this area, this volume, and it has some other charge and some other volume. So we say that it has a charge of Q dash and it has a volume of V dash. Now what will be this volume? This volume will be 4 upon 3 pi R cube. Why? Because this distance now is R. The distance of the Gaussian surface from the center is R. So now what is the direction of electric field in area vector? Now this is the area. Area vector will be always radially outward from the surface, and so will be the electric field. So electric field will be radially outwards, which is true for every spherical surface, and so will be the electric field area vector also. So if electric field is in this direction and we are talking about a small area, let us say this, then dA vector will also be in the same direction. So E vector is parallel to dA vector. The situation is same for the area vector and dA vector. You know, for a sphere, area vector and dA vector, they will always be parallel to each other. So again, integral of E vector dot dA vector will be, E will be constant on this surface, so it will be E into 4 pi R squared. And charge enclosed now. The charge enclosed is different to Q. In this case, the charge inside this sphere, which is red colored, is Q dash. Okay, but Q dash is not mentioned in the problem, but what is mentioned is the charge density. Charge density is Q upon V, which will be Q dash upon V dash. So it will be Q upon 4 upon 3 pi A cube will be equal to Q dash upon 4 upon 3 pi R cube. From this equation, Q dash will be Q, cancel, these cancel. Q dash will be equal to Q R cube upon A cube. And therefore, now if we use Gauss's equation, it will be integral of E vector dot dA vector is equal to charge enclosed divided by epsilon naught. So we have this, and we know what is Q dash, and charge enclosed is Q dash. Okay, so it will be E4 pi r square Q r cube upon a cube into a constant epsilon naught. So now this will cancel with this, and 1 r is left, so it will be E is equal to Q upon 4 pi epsilon naught r and a cube. So this will be the electric field due to at a point which is less than a, okay, inside the sphere. This point is outside the sphere. Now let us check these for different situations. Let us say that for the first situation, what is the electric field at the center of the sphere? Okay, so at r is equal to 0, electric field will be 0. So this is good. But if this was true inside the sphere, r is equal to 0, electric field will be equal to infinite. So it means that this is not valid for a point which is inside the sphere. Now, at the surface, what will happen at the surface? Let us say that at the surface means r is equal to a. And if r is equal to a, electric field will be given by Q upon 4 pi epsilon naught a squared. And from here, E is equal to Q upon 4 pi epsilon naught a squared. So both of these, they agree at the surface. The electric field is same. Okay. So for inside the sphere, this is valid. For outside the sphere, this is valid. Okay. And we need to understand this also, that if R will increase, electric field will decrease. So if I have to draw a graph for electric field in R vector, how will it look like? So it means that we are starting from the center of the sphere. So if this is electric field, this is R, and here the electric field and the R is 0. At R0, electric field is 0, and then as you increase R, it will increase. Okay, so this will be the point where R is equal to A, and then after that, if R will increase, electric field will decrease. So here the electric field will decrease. Okay, so this is the situation where R is less than A, and here R is greater than A. Okay, so and here R is greater than A. So for R greater than A, electric field will be given by Q upon 4 pi epsilon naught R squared, which is this one. And for R less than A, electric field will be given by QR divided by 4 pi epsilon naught A cube.